Hi guys, welcome to another one of RT Dowlett lectures, and today I want to be focusing on CSEC physics, and I will be looking more specifically at momentum. So today we're going to be focusing on the objectives according to the CSEC syllabus. So the first thing we want to talk about is what is momentum. Now, momentum is symbolized by common P, and it is defined as the product of mass and velocity of a body. And many times in past paper questions, you will be asked for about 2 marks for the definition, and you get 1 mark for terming it product and the second for saying mass and velocity. Now it is a vector quantity, and that means that direction matters. So it means that when you are looking at momentum, you will have conventions of positive and negative. So P is equal to mv, and of course the unit is a combination of the units of mass, which is kilogram, and velocity, which is meter per second. Now the context of momentum in physics is collisions, and when we talk about a collision, you are talking about 2 bodies hitting each other. Right? So you can have many different types of collisions in terms of how the body behaves. The 2 main categories of collisions are elastic collisions and inelastic collisions. So it's not an explicit objective to know the difference at the CSEC level between elastic and inelastic. It is a CAPE objective. However, the theory is not difficult, so you can understand it as you're doing the topic now. So when you talk about an elastic collision, you are talking about total momentum is conserved. In an inelastic collision, you will also have total momentum is conserved, and we will look at conservation of momentum just now. You're going to say that the total energy is also conserved. And in an inelastic collision, the total energy is conserved. What is the difference is that in an elastic collision, the kinetic energy is conserved. But in an inelastic collision, the kinetic energy is not conserved. So what that means is that if I look at the kinetic energy, which is a half mv squared of each body before they collide, and I add them up, and I look at the half mv squared, the velocities of the body after they collide, I find a half mv squared after, and I sum it up, they will not be equal. So now let us look at the law or the principle of conservation of linear momentum. The law or the principle of conservation of momentum states for 2 or more bodies involved in a collision, the total momentum before the collision is equal to the total momentum after the collision. All right, so let's do an example. And again, I always tell my students that they will give you the situation in terms of, they will tell you how the bodies are behaving. Are the 2 bodies moving in the same direction before the collision? How they behave after? So it is not a set scenario that you learn of. It is situational, and it is given in the exam. So let's look example 1. So let's say I have a ball, and the mass of this ball is 2 kilograms. It is moving with an initial velocity u1 of, let's say, 2 meters per second. It then collides with a bigger body, let's say a 3 kilogram mass, and this mass is at rest. Now, after the collision occurs, you would find now that the 2 kilogram mass remains at rest and the 3 kilogram mass moves off with some velocity v. Now, because you are talking about a vector quantity, I typically tell my students, choose a direction of positive. So I like to go taken to the right as positive. But again, you could have taken to the left. It just means that when you are looking at the velocities, you would have to have your conventions accordingly. So the initial momentum of the 2 kilogram body is mv, which is 2 by plus 2 because it's in this direction to the right. And I'm adding it because according to the principle of conservation, you are summing up your momentums, right? And when the second body is at rest, it becomes 3 by 0. So it's 4 plus 0, which would give me the total momentum before of 4 kilogram meters per second. Now, after the collision, you were told that the 2 kilogram body comes to rest. So your final momentum of this body is 0, 2 by 0, and 3 moves off with some velocity v. So the expression for my momentum after is 3v. So equating or using the principle, the total momentum before is equal to the total momentum after. So then it implies now that 4 kilogram meters per second is 3v. So v is 4 over 3 meters per second. Now, because this convention is positive, that's important because it implies that the second mass, m2, is moving to the right. If I had solved it and I had gotten a negative answer, right? Again, I had assumed here that the body was moving to the right. But if it did not, based on the values in the question, then I would have gotten a negative answer. And the negative answer would just imply that my body would have been moving to the left, because that is what a vector quantity encompasses. Direction is important. A convention of positive, right, will show your body is moving in one direction. A convention of negative is in the other. All right, let's look at a second example. So this example 2 would imply a head-on collision. So in a head-on collision, you have the two bodies moving to face, right, towards each other. And again, I am choosing at the beginning of my question which direction is positive. So let's consider M1, same 2 kilograms, moving now with a velocity of 2 meters per second, and it's colliding with another mass, M2, 3 kilograms, moving in the opposite direction with a velocity of 4. So they have told you in the exam, after they collide, right, they stick together and they move off with a common velocity v, right? So you don't know where v is, if it's to the left or to the right. So you're assuming that momentum is conserved. So let's get the total momentum before. In order to get the total momentum before, I'm taking the mass and velocity of each body and I'm multiplying it. So because this is going in my direction as positive, I put plus 2. Because now this 4 is moving opposite, I put negative 4. So 2 by 2 plus 3 by minus 4. So I get 4 plus minus 12, which is minus 8. Now it's fine if you got a negative momentum before. Right, so let's work on now the momentum after. So because the two bodies have stuck together, I have a combined mass of 2 and 3, which gives me 5 kg, and it's multiplied by some velocity v. So therefore, I have now momentum before is equal to momentum after. So minus 8, remember you're using your convention, these are vector quantities, is 5v. So v now works out to be minus 8 over 5, which is minus 1.6 meters per second. So if this is the case, when we go back here, you are realizing that v is actually to the left. because it implies the negative sign. So that's why I told you, you don't even have to assume. Let the question help you. Because if you get a positive value, it means your velocity is in the direction that you had considered it before. If it is negative, it means it is opposite.